Most welcome to lecture number 14 of my series on Introduction to Complex Analysis. In this video, I shall discuss about Cauchy's integral formula. And as a prerequisite, we will use the proposition that you can see on your screen. Let me remind you, I have discussed this proposition in detail in my previous video on Cauchy-Gauss theorem for multiply connected regions and some of its consequences. If you have not watched that video, I would recommend you to watch that one before you start watching this one. The link is in the description below and you can see above as well. The proposition says that let Fz be analytic in a region bounded by two simple closed curves C1 and C2 and on these curves, means Fz is analytic on these curves as well. Then integration of Fz along C1 is equal to integration of Fz along C2, where C1 and C2 are both traversed in positive sense relative to their interiors. In simple words, if Fz is analytic on C1 and C2 and the region as you can see in the diagram on the right side, then the integration of Fz along both these curves will be equal. Now we will use this proposition to prove Cauchy's integral formula, which says that let Fz be analytic inside and on the boundary C of a region R which is simply connected and A is an interior point of R. Then f of A will be equal to 1 upon twice pi I into integration of Fz by Z minus A along the curve C. You can understand here that the function Fz divided by Z minus A is analytic inside and on the curve C except the point Z equals to A. Now let us consider a circle centered at A and radius epsilon which lies totally within the region R. Finding such a circle is possible because A is an interior point of R. So let us consider the circle is given by gamma. Now it's quite clear that the function Fz divided by Z minus A is analytic on C gamma and the shaded region bounded by gamma. So by virtue of the proposition that we have stated above, can you understand what we can write? Absolutely correct. We can write that integration of Fz divided by Z minus A along C is equal to integration of Fz by Z minus A along gamma. Now, remember that this gamma is a circle centered at A and radius epsilon. So, gamma can be written as Z minus A is equal to epsilon e to the power I theta, where 0 less than or equal to theta less than twice pi. That means any point Z on gamma can be expressed as A plus epsilon e to the power I theta, where theta will be something lying between 0 and 2 pi with open in the 2 pi side. And this implies dz is also I epsilon e to the power I theta d theta. So if we plug in everything in this inequality, what do we get? That integration of Fz divided by Z minus A along C is equal to f of Z. That means f of Z means A plus epsilon e to the power I theta divided by Z minus A. That is epsilon e to the power I theta and d theta. dz is I epsilon e to the power I theta d theta. Now, if you closely inspect these things, this epsilon gets cancelled. This e to the power I theta also gets cancelled. So what we get, let me have some space here. We get that this is equal to I into integration. Sorry, I forgot to plug in the limit for theta. The limit for theta will be from 0 to twice pi here, because you can see that theta varies in between 0 to twice pi. So I into integration 0 to twice pi uh, f of a plus epsilon e to the power I theta d theta. So this is what we are getting as a simplified version. Now, if we make the circle smaller and smaller, that means when this epsilon tends to 0, taking limits on both the sides, we get limit epsilon tends to 0, integration fz divided by z minus a dz is equal to limit epsilon tends to 0, I into integration of f of a plus epsilon e to the power I theta d theta. Now, taking care of the fact that this limit is on epsilon and the integration we are doing with respect to theta, they're completely independent of each other. Therefore, we can simply interchange the two operators and we can write this as equal to I into integration of 0 to twice pi limit epsilon tends to 0 f of a plus e to epsilon e to the power I theta d theta. That's it. Now, if we consider that this function f is continuous, it is analytic. So the function f is continuous in this on this as gamma. That means the function is continuous in this entire range also. So we, if we use the continuity of this f, we can write this as equal to I into integration of 0 to twice pi f of, if I use the continuity of this function f, then that means the limit we can bring inside, and if we bring the limit inside, here epsilon is tending to 0 and here I have epsilon, so this will result to f a d theta. Yes. Now, if we do the integration considering the limits 0 to 2 pi, what I will get? We will get this is equal to I into f of a is a constant, I can take it out. So this is integral 0 to twice pi d theta. So that means the result of this integration will be twice pi. So I can collectively write this as twice pi I into f of a. Therefore, what we are getting? Therefore, we are getting that now in this side, if you consider there is no epsilon in this part. So that means this is simply, this results to integration fz by z minus a dz along c. And if I bring this twice pi I in this side, I can write the whole thing as f of a is equals to 1 divided by twice pi I integral along c fz divided by z minus a dz. So we have got the formula which we were trying to derive. So this is our Cauchy's integral formula. Now this formula can further be extended, and under the same conditions, we can further derive that if prime a, that is the first order derivative of fz at z equals to a, is equals to 1 by twice pi I integral along c fz by z minus a whole square dz. We can further prove that the second order derivative of fz at z equals to a is equals to 2 by twice pi I integration along c fz by z minus a whole cube dz. And in general, in this way, we can prove that the nth derivative of fz at z equals to a is equals to factorial n divided by twice pi I into integration of fz by z minus a whole to the power n plus 1 along the curve C. So these can be used for solving lots of problems. This will be extremely useful, and this also tells us about a very interesting result that if a function of a complex variable has a first derivative that is analytic in a simply connected region R, then all its higher derivatives exist in R. This is not necessarily true for functions of real variables. Now, let us solve some problems using this Cauchy's integral formula. Find the value of integration along C dz by z square plus 4 whole square, where C is given by mod z minus I is equals to 2. Now, can you tell me what is C? C is a circle with center at I and radius 2 units, something like this. Now here, if we consider this denominator z square plus 4 whole square, this can be expanded as z plus twice I whole square into z minus twice I whole square. Therefore, I can write this integration dz up on z square plus 4 whole square along C as equal to integration along C 1 up on z plus twice I whole square divided by z minus twice I whole square dz. So I'm trying to identify this function as my fz, what I have discussed in the Cauchy's integral formula. So this is in the form fz divided by z minus a whole square dz. Now we need to understand where this point A, that is twice I, lies. So if you look at the picture, then we can understand that twice I will lie somewhere like this. That means inside this curve C. So, and this C, and on this curve C, the function 1 divided by z plus twice I whole square is analytic, and moreover this function is analytic in the whole region, simply connected region bounded by this C as well, if we consider it in that way, because the singularity of the function fz, small fz, that is 1 upon z plus twice I whole square, is at the point z equals to minus twice I, which will somehow lie here outside my curve C. So on C and inside C, that means on the simply connected region, I'm making some yellow dots on that region. The function fz, that is 1 up on z plus 2I whole square, that is analytic. So we can comfortably apply Cauchy's integral formula. And if we apply Cauchy's integral formula, then we know that by Cauchy's integral formula, integration along C fz divided by z minus a whole square dz will be equal to what? Let us quickly revisit this Cauchy's integral formula. Yes, this will be this is in this form. So this will be equal to twice pi I into the first order derivative of fz at z equals to a, that is f prime a. So this is my formula. Therefore, if I apply this formula here, what I'll be getting, I'll be getting this integration is actually equal to twice pi I into the first order derivative of fz at z equals to a as per the formula. Now here this numerator is my fz. So the first order derivative of this fz at z equals to a. That means I am simply writing f prime and a is twice I. So f prime twice I, where fz is given by 1 upon z plus twice I whole square. Now, if you calculate, you can see that this calculation will lead to twice pi into what is the first order derivative of this fz? That will be first order derivative. So 2. So this is minus 2 divided by z plus twice I whole cube at z equals to twice I, and that will be equal to twice pi I into if you plug in the value z equals to twice I, what I'll be getting into 64, so 1 upon 32I. So this I will get cancelled, this will cancel, and I get a 16 here. So this is equals to pi divided by 16. So this is our answer. So pi divided by 16. This is our answer for this integration. Now the next problem will remain as your homework, which says use Cauchy's integral formula to find the value of integral along C z plus 4 divided by z square plus 2z plus 5 dz, where C is given by the curve mod of z plus 1 minus I equals to 2. So I'm keeping this problem as your homework. I'm pretty sure you all can solve it. Solve this problem. Let me know the answer in the comment section below. I'll be expecting an answer from you all. So that's it for this video. In the next video, I will discuss about power series expansion of a function of a complex variable. And we will specifically discuss one by one two important power series expansions, the Taylor series expansion and the Lorentz series expansion. And you will see that this Cauchy's integral formula will be used in those power series expansions also. So see you again in the next video. Take care.